To get to the heart of what this lesson is all about, we'll begin with some of the things that we already know from our earlier work in calculus. I want to start off with just a quick rehash of some of our derivative work. If f of x is equal to x cubed, then we know by the power rule that f prime of x is 3x squared. If f of x is 5x to the 6th, then by the power rule we know that the derivative f prime is 30x to the 5th. Again, by the power rule, if f of x equals x to the 1/2, the derivative is 1/2 x to the minus 1/2. If f of x is equal to 5x to the minus 2, by the power rule, the derivative is minus 10x to the minus 3. We've talked some about derivatives of exponentials. We know that e of x is its own derivative. So if f of x is e to the x, we know that the derivative of e to the x is e to the x. If f of x is equal to e to the 2x, then we have to use the chain rule on our basic exponential rule to say the derivative is e to the 2x times the derivative of the exponent, which is 2. So we get 2e to the 2x. We know about simple logarithmic derivative. If f of x is equal to the natural log of x, then the derivative is 1 over x. Got something slightly more complicated. If f of x is equal to the natural log of 2x plus 1, then by the chain rule applied to the log rule, we know that we get the derivative of what you're taking the log of over what you're taking the log of. In other words, if you think of 2x plus 1 as the log of u has a derivative, u prime over u. U prime would be the derivative of 2x plus 1, which would be 2 over 2x plus 1. These are all things we already know. Nothing new here. Should be old hat. Can we take these things, though, and go in the other direction? What if I covered up what the function was, showed what the derivative came out to be, and asked you to go backwards? Could you go back and figure out what the function was that produced that derivative? This is the major subject of this lesson. Let's try it. Well, you could actually just look back and see that if the derivative is 3x squared, the original function was x cubed. But if you imagine that that wasn't there, you'd have to think about reversing yourself. When you take the derivative, you reduce the exponent by 1 and multiply by the original exponent. When you're going backwards, you'd have to reverse that. So the 2 that you see would originally have been a 3. And you've got to think about what happens. The 3 in the function, the f of x part, the 3 in the exponent, goes down front, and that's where this 3 comes from, and the 3 goes down to a 2. So when you're reversing yourself, the exponent has to go back up to a 3, and you can see that that 3 in front is the original power. So start thinking about how you'd reverse. Let's do another. If the derivative came out to be 30x to the 5th, what was the original function? Well, first of all, the exponent 5 would be a 6, and remember that 6 gets brought down. But we want a 30, not a 6, but 6 times 5 is 30, so that means there must have been a 5 there originally. Think about how your brain is going through this process of figuring out how to go backwards. This is very important. Another one. We end up with the power of negative 1/2. We know that when we go backwards that the power is going to be one higher. So if you take 1 and add it to minus 1/2, you get positive 1/2. And if you think about it, when you're taking the derivative of this, the 1/2 is going to come down front, and that's where this 1/2 comes from. I want you to think about what you're doing to go backwards. This thought process is very important. Well, another. If you end up with a derivative of minus 10x to the minus 3, the original function must have had a 1 higher exponent, which is minus 4. One higher exponent, which would be minus 2. Don't go the other way. Minus 3 plus 1 is minus 2. And in order to get a minus 10, that minus 2 had to multiply by something to give the minus 10, so it must have been a 5. Well, e to the x is its own derivative, so if you had something that gave you an answer of e to the x, it must have been e to the x. That's easy enough. But if you had 2e to the 2x, you know that when you take the derivative of a simple exponential, you get the same exponential back, and it may be multiplied by something. So you know there's going to be a 2e to the 2x, and the answer is just a question of, is there more? If you think about it a minute, no, because the chain rule says when you take the derivative of e to the 2x, you get e to the 2x, but then you have to multiply by the derivative of the exponent, and that's where the 2 came from. So you got to think about when you're going backwards, what was there to start with. Quickly, the last two, 1 over x is obviously natural log of x, and this one, well, again, you could just look back and see, but why is it that? The derivative of 2x plus 1 is 2, and the derivative formula for the log derivatives is u prime over u, so it must have originally been natural log of u, where u was 2x plus 1. You might find a few of these harder to work backwards than others. That's okay. We're going to have some tools that make it easier. But what I'm emphasizing here is the thought process. At least get you thinking about what you have to go through to reverse these operations. Going from derivative to antiderivatives is what we've done. Now we're going backwards from antiderivatives to derivatives, and it requires the mindset of figuring out what the original function was, whose derivative is what you're given. So keep that in mind. I want you to develop this mindset. Now, this idea of reversing the differentiation process is very important. And at least for now, we're going to call the process antidifferentiation. We actually will rename it later, but right now we would just call it antidifferentiation. You can also use the term derivative and antiderivative to describe the results of carrying out this process. Of course, the derivative means going in one direction, the antiderivative means going in the other direction. For example, just like I can say that 3x squared is the derivative of x cubed, I can also say that x cubed is an antiderivative of 3x squared. Again, this idea of going one way and then reversing yourself is what you should be thinking about here. You might wonder why I say an antiderivative instead of the antiderivative. If you're not wondering that, maybe you should be. There is a reason, and it's related to this fact. If I gave you the function f of x equal to 6 and asked you what the derivative was, I'm quite sure you would say 0. But isn't it also true that if I told you that f of x equals 14, the derivative would be 0, and that if I told you f of x equals negative 7, then the derivative would be 0? Can you sort of see what I'm getting at here? The derivative of every constant is 0. So when you're trying to reverse yourself from a 0 going backwards, you can't really know what the result is. Is it 6? Is it 2? Is it 14? Is it negative 7? And the answer is we just don't know. So instead of saying that the antiderivative of 0 is a particular constant, we just invent the letter c and call it c. And so the antiderivative of 0 is c, where c just represents whatever constant you want it to be, because any constant has a derivative of 0. Again, this idea of thinking backwards. The derivative of a constant is 0. The antiderivative of 0 can be any constant, so you have to incorporate that into your thinking. But the important takeaway from all of this that we've just discussed on this slide is that the antiderivative of 0 is just say it's c, thinking in your mind that c is just a constant. You don't know what it is. It's an unspecified constant. Now, before we go any further, I want to introduce some notation. If we start off with a function f, we're going to capitalize that letter to indicate the antiderivative. Okay, so if I use G, it would be capital G. If I use H, it'd be capital H. Whatever I capitalize, I'm going to use that capital letter to stand for the antiderivative of that function. So for example, if I said f of x is equal to 2x, then capital F of x would be x squared, because x squared has a derivative of 2x. So that means 2x has an antiderivative of x squared. And again, I'm saying an antiderivative because we know that we could add any constant and it would still be correct. If g of x is 1 over x, then the antiderivative, capital G of x, would be the natural log of x. We still haven't incorporated or formalized, maybe I should say, the procedure for handling this issue of not knowing what the constant is, and we're going to get to that now. If we just go back to that f of x equal to the x, then capital F of x equal x squared example, we're going to add a constant to it, because if little f of x is 2x, then capital F of x could be x squared plus 1. It would still have a derivative of 2x. It could be x squared plus 3. It would still have a derivative of 2x. It could be x squared plus minus 5, and it would still have a derivative of 2x. So what we have to do is just say we're going to add plus c. Whatever the original function started off being, when we take the antiderivative, we just put a plus c on the end. And that plus c indicates our knowledge of the fact that it could be plus any constant. Or, of course, if it's negative, you can think of it as plus a negative, which is minus any constant. Think about that and the implications of that. Now let's use this notation and get you used to it a little bit. Just go back to some of the ones we've done earlier. If f of x is equal to 3x squared, what is capital F of x? Well, remember the capital means the general antiderivative. So you take the power goes up to a 3, and if you think backwards, the 3, you're taking the derivative, the 3 comes down, and that's where this 3 comes from right here. But you have to put a plus c because we want the general antiderivative, acknowledging the fact that if you had any number there, 5, 7, 13, negative 5, even pi, its derivative would be 0. And so you would still be back to this 3x squared. I'm trying to get you used to the notation now, though. You capitalize the letter, add a plus c after you write down a particular antiderivative. And again, if you're ever confused about, well, did I do it correctly or not, all you've got to do is take the derivative of what you ended up with and make sure it gives you back what you started with, and you can see that it does. And that gives you confidence that you did it correctly. How about this one? If f of x equals 2 e to the 2x, what's capital F of x? Well, again, this is one we did earlier. We want the general antiderivative. We know it's going to have a plus c. We know that when you take the derivative of e to a power, you get e to the power. So if you take an antiderivative of e to a power, you're going to get e to that power as well. But you might have a constant out front, and if you think about it, the chain rule says that when you take the derivative of e to a power, you write down e to the power, but then you come back and multiply by the derivative of the exponent, and the derivative of 2x is 2, and that's where that 2 comes from. Again, don't sweat too much about the details. I want you to understand the conceptual idea that you're going back in reverse. Derivative to antiderivative, as opposed from what we've been doing, which is going from function to its derivative. And again, if you're ever in doubt that it's right, all you've got to do is check it. If you take the derivative of what you get, if it comes out to be what you started with, then you know that you did the antiderivative correctly. But it's the thought process here that I'm trying to emphasize. Now we just did this one. If little f of x is 3x squared, then capital F of x, the antiderivative, is x cubed plus c. But what if I gave you something slightly different? What if I took the 3 away and just said, if f of x equals x squared, what is capital F? Well, think about that a minute. We know that the exponent has to be 3 because when you take the antiderivative, the exponent reverses. Instead of going down by 1, it goes up by 1. So we know it's going to be a 3. But the question is there a coefficient of that 3? And if you think about it a minute, you know that if you're looking backwards, you know when you take the derivative of x cubed, you're going to get 3x squared. But you don't want that 3 there. Notice in the original problem, the 3 was there and we wanted it. But this time, the 3 is not there. There is no 3 there, so we don't want it. So what you have to do is go back up and compensate. If you don't want the 3, you've got to multiply it by 1/3, so you have to put a 1/3 out front. So that you don't have to end up with a 3 in the coefficient position. And then you have to add a plus c, always. And again, as with the others I said, if you have any doubt that you did it right, all you've got to do is go back and check it. If you take the derivative of the answer you got, see what happens. The derivative of 1/3 x cubed, the 3 comes down and multiplies by the 1/3. 3 times the 1/3 is 1. Remember, I wanted that 1/3 there for that exact reason. So 3 times 1/3 would just be 1 because I only want a 1 to be here. I just want a 1 to appear there. And then, of course, the derivative of a constant is 0. And you can see it works. What I'm doing now is sometimes called guess and check. You sort of guess what the antiderivative is, and then you check it out and take the derivative going backwards. And if you need to compensate by something, you can. I call that guess and check. And it's really a very effective way to do simple antiderivatives. But don't worry, if that's frightening you a little bit, we will have some formulas that you can help to bolster your intuition with. But for right now, we're sort of doing this guess and check. But you can see that the result, if you work backwards, does give you what you started with, so you know you got it right. At least that's an advantage of doing these problems. You can actually take the derivative and go backwards and check to see that you're right. Okay, let's sort of just wrap up where we've gotten so far. If little f is the function, capital F is the general antiderivative, it always has to have a plus c. As I said a minute ago, we got this result by what I like to call guess and check. If you become good at that, it can really be an effective way to take antiderivatives, and I highly recommend it. But don't worry if that is hard for you. First of all, you might get better at it. And secondly, we will develop some formulas very shortly that will help bolster your ability to do this without having to do so much of this guess and check. So, there is a formula. I've alluded to it a couple of times now. And this is all it is. This is writing down what we've been doing so far, basically. It says if you start off with a function that is a number times x to a power, as long as n is not -1, and we'll get to that in the future, why n can't be -1. But for now, if you have f of x equals a times x to a power, the antiderivative is always going to be, of course it's going to have a plus c, but beyond that, the exponent goes from n to n plus 1, it goes up. You've got to put a fraction out front that has n plus 1, that same exponent in the denominator, and then whatever coefficient was there stays there. And that gives you a formula for what we've actually been sort of doing, that guess and check. This sort of formalizes that. And I'll show you how easy this really is. Let's take that formula and practice it. It's really just the antiderivative analog to the power over derivatives. It's just the power over derivatives turned backwards. Instead of subtracting 1 from the exponent, you're adding 1. Instead of multiplying, you're dividing. It's the analog of the power over derivatives. So let's do a few. If I ask you to find the antiderivative of f of x equals 2x to the 5th, using that formula, The first thing I think is this. This exponent 5 is going to have to be bumped up by 1. So that 5 is going to turn into a 6. And then according to the formula, whatever you bump the exponent up to is going to have to appear in the denominator. So that's why I put a fraction with no denominator. The 2 just carries along for the ride, and the denominator is the same thing that the exponent is. And then, of course, you have to have a plus c. And 2/6, of course, is 1/3. This is not difficult. And the bonus is you can check it very quickly by taking the derivative of 1/3 x to the 6th plus c and making sure that it really does come out to be 2x to the 5th. So you've got a nice formula for powers of x, and then you've got a quick way to double check and make sure you didn't make a careless mistake. Win-win. How about this one? X to 1/2. Well, again, if you use that same rule, you're going to increase the exponent by 1. That exponent is going to be in the denominator of a fraction in front, and whatever was in front stays there. Well, in this case, there's just an understood 1 there, so it'll be 1 over. So you're going to, think of this as being an understood 1, so that 1 goes in the numerator. This power of 1/2 is going to have to be bumped up by 1. So if you take 1/2 and add 1 to it, you'll get 3/2, and then the denominator of that fraction out front is going to be whatever the numerator, whatever the exponent was. So that would be 3/2. Now you really need to get good with some of these simple ideas with fractions. If you take 1 over a fraction, if you divide by a fraction, it's like multiplying by the reciprocal. So 1 over 3/2 is simply like turning the fraction upside down, it becomes 2/3. And of course you have to put a plus c. So the 1 over 3/2 is like flipping the fraction, becomes 2/3. The 1/2 power went up to 3/2, and then you have to have the plus c to indicate that it's a general antiderivative. And you can take the derivative and go backwards and double check it if you have any doubt. I hope you're beginning to feel like this is not so challenging when you really think about what you've got, what kind of tools you've got to do these. A lot of the things you learned about derivatives is going to follow directly through by antiderivatives, one of which is because we know we can differentiate a multi-term expression term by term, follows that you're going to be able to do the same thing with antiderivatives too. And as an example, let's do this one. If I gave you f of x equal 2x to the 5th minus 3x plus 2, that's a 3-term expression. All you have to do is use the formula term by term by term. So using the formula on the 2x to the 5th, you increase the power by 1, divide by that power, and the 2 just stays there. Similarly, for 3x, it's going to be 3 stays where it is. It's going to be x squared divided by 2. And I hope you don't even need a formula for going from 2 to 2x. The derivative of a constant is 0. That should just be second nature. The antiderivative of a constant is the constant times x. That should also be second nature. If you did want to use the formula for that, you'd have to think of 2 as 2x to the 0, because 2x to the 0 is 1, and then use the formula on that. But I really don't recommend that. I just think you should remember that the derivative of a constant is 0. The antiderivative of a constant is the constant times x. Much simpler than thinking of it as an application of that formula there. And then, of course, you always have to have a plus c. There's also another situation I want to point out. We've done this before, but I want to particularly point it out here. Sometimes we can take an expression that's not written as just a literal sum of terms, but after doing something to it, we can turn it into a sum of terms. And this is a type of problem I'm talking about here. What if I have a multi-term numerator like 2x cubed plus 1 and a single term in the denominator, which is x squared? We've come across this kind of thing before. We can turn that into a 2-term expression by breaking the fraction up. We can take the 2x cubed divided by x squared plus 1 over x squared, make it into a 2-term expression. That's 2x cubed over x squared plus 1 over x squared. The x squared goes into the x cubed and just leaves 2x in the first term. And then, of course, 1 over x squared is x to the minus 2. Now we can use our antiderivative rule on each one term by term. When you do it to 2x, you get 2x squared over 2, which is just going to be x squared. And then when you add 1 to minus 2, you get minus 1, but then you divide by minus 1. And again, that's an understood 1 in front of the x squared. And so you get 1 over negative 1, x to the minus 1. And 2 divided by 2 is just 1, so you get x squared. And 1 divided by minus 1 is just minus 1. So you end up with x squared minus 1, x squared minus x to the minus 1 plus a constant. So this little trick, when you see a multi-term numerator but a single-term denominator in a fraction, is really neat, and it's very useful for taking these simple antiderivatives. Now, I do want to say one thing. This rule obviously will not help us with exponential and log expressions. We did a couple of simple ones earlier, but that's not really what this lesson's about. We'll get to that in later lessons. You can reverse yourself on these simple logs and exponentials just based on your knowledge of derivatives. But this lesson is really about taking antiderivatives of x to powers. We'll get to more complicated stuff later. Now, we introduced this capital letter notation for an antiderivatives. It's quite frequently used when you're first talking about antiderivatives to just get you used to the idea of computing antiderivatives. But we typically move away from that notation pretty quickly to something that looks rather strange. I think it's the reason that this capital letter notation is actually used so much in the beginning, is to allow you to separate the awkward notation from the much simpler concept of doing an antiderivative. If you were transported back in time to the days of Isaac Newton and Gottfried Leibniz, or if you took a course where you studied some of the ideas that led up to the invention of calculus, we could better handle why this notation came to be what it is. But we're not going to do that. So, as strange it may look, I'm going to introduce this notation without any further explanation, and you just need to get used to it, and the fact that even though it's a strange looking notation, it's not difficult. You just have to get used to seeing it, and then you've got to learn how to use it. And basically we've already done that. The notation now comes as a replacement for the old capital letter notation. If you are, however, interested in learning more about where that notation came from, I gave you a couple of YouTube links that you're welcome to go to. It's really quite interesting. Anyway, the bottom line is the symbol that we actually use more often than anything else for antiderivatives is called an integral symbol. The process of antidifferentiation is quite often called integration. And you've got this elongated S-looking symbol that's called an integral sign. And it's the sign that tells you you're going to be taking an antiderivative. Again, I'm not going to get into why that notation came out to be what it is. Simply getting you used to seeing it and then explaining that it's nothing more than the old antiderivative now that we've been doing for these last minutes. And this is it. The expression below is called the indefinite integral of f with respect to x. It's that elongated s, that integral sign on the far left, paired with a dx on the right, and in between the two is the function that you want to take the antiderivative of. And that's simply what we were calling in our old notation capital F, which is the general antiderivative. So when you see that notation, integral sign on the left, dx on the right with a function between it, it's just asking you to take the antiderivative, just like we've been doing for the last minutes. And like I said, this symbology simply means the antiderivative, the general antiderivative. So you can think of that symbol as just another way of saying take the antiderivative of the function enclosed. So the symbology seems sort of strange, but the process is nothing more than what we've been doing, and I want to prove that to you. So let's take this symbology and emphasize what each thing is, and then let's just do some problems. The elongated S looking symbol is called the integral sign. The thing after that, the function that you're going to take the antiderivative of, is called the integrand. The dx following the integrand is called the differential. The capital f of x plus c is just the general antiderivative that we dealt with earlier. So once you've come to grips with what the symbology means, the practical use of it is nothing but what we've already done. So just try to get used to seeing that symbol and remembering it's just antiderivative. And that plus c by itself is called, the constant of integration. It is absolutely crucial for you to understand that the integral sign and the differential symbol always pair together. You never have an integral sign without the differential. You never have the differential, at least in this context, without the integral sign. It's sort of like left and right parentheses. You think of the integral sign as being a left paren and the dx as being a right paren. You never see a left paren without a right paren. You never see an integral sign without a dx, at least in this context of integration. Now, we've stated the power rule for antiderivatives in terms of our capital F notation, but if you want to put it in the notation of the integral sign, we could take that same expression, ax to the n, and put it in between the integral sign and the differential, and that would lead us to the same formula we had before. So this is nothing new practically. It's only a new notation for what you already know how to do or are learning how to do. And let's just prove that. Let's go back to some of the previous examples and use that new notation. So instead of calling the one function little f and say find capital F, I'm just going to take the function that I want to take the antiderivative of and put it inside of my new symbology, an integral sign on the left and a dx on the right. And that simply says find the antiderivative of 3x squared. Now, how many times have we done that already? But if you want to apply the formula, the 2 goes up to a 3, then you divide by the 3, and the number in front stays where it was. But we've done that so many times now, I hope you've memorized it. The antiderivative of 3x squared is x cubed plus c. Another way of saying that is the integral of 3x squared is x cubed plus c. So more and more as we go through this, we're going to be increasingly dropping the word antiderivative and substituting the word integral. They mean the same thing. What's the integral or the antiderivative of 2x to the fifth? Well, again, using your formula, you bump the 5 up to a 6 and divide by it, and the 2 that was in front stays there. And of course, 2/6 reduces to 1/3. This is the same old thing. Again, we talked about the antiderivative of constant. It's just the constant times x. So the integral of a number, 7 in this case, is just going to be 7x. Don't forget the plus c. Not difficult at all. Just got to get used to the symbology. And remember, as I said numerous times now, you can check all your answers by differentiating them. How about this? The integral of the square root of x. Well, remember, that's just the antiderivative, and we know that when we're working with radicals, we change them to fractional exponents. So the first thing you'll do is write the square root of x as x to the 1/2, and then you can apply the rule, which says you add 1 to the exponent and divide by it. Well, if you add 1 to 1/2, you get 3/2, and then you divide by 3/2. But 1 over 3/2 is simply like multiplying by the reciprocal, so 1 over 3/2 is 2/3. So you get 2/3 x to the 3/2 plus a constant of integration. This is not difficult. How about this one? Well, that's a binomial squared. Squaring a binomial out is not very hard, But we don't have a formula yet that says if you've got a function of x to a power, so really our choice is to not be able to work this or just square it out. So we're going to take 2x plus 1 times itself and just square it out. So you will take 2x plus 1 times itself, 2x plus 1. And you'll use the FOIL method on it, first outer, inner, last. And you'll end up with 4x squared plus 4x plus 1 inside of the integration symbols. And now you can do it term by term. So you take 4x squared and use the formula. That'll bump the 2 up to a 3 and divide by 3. The 4 stays where it is. In the second term, it'll bump the 1 up to a 2, divide by 2, and the 4 stays where it is. And then again, we've talked about this. The antiderivative or integral of a number is just the number times x. And since the number is 1, you get 1 times x, which is just x. And then, as always, you put the plus c there. The only thing I can think of, maybe to simplify a little bit, is to write 4 over 2 is 2. This is not difficult, but you do have to have your mind right. You got to think about what you're doing, and you got to remember what the symbols mean and practice. I'm not going to go through these one-on-one because most of these are just common sense things. The first one just says when you take the integral of a constant, you get the constant times x. I've said that several times. If you have a constant multiplied by a function, you can just let the constant sit there and take the antiderivative of the function. We've done that with derivatives, and it's going to work the same way with the antiderivatives. If you've got two functions added together, you can do them separately. We've been talking about that. Or if it's subtraction, again, you can do them separately. And this fifth formula is actually what we've been doing. I wrote it slightly differently. I went ahead and put the a in there, and they didn't. They're using the fact that if there's an a in there, you can just leave the a there and multiply it in the end. So whichever version of that formula you prefer, it's fine by me. It works either way, whether you don't put the a in there or whether you do. Comes out the same in the end. So that's sort of something you refer back to if you need to, but really a lot of this is intuitive. I think once you practice, you start doing some of these properties without even realizing you're doing them. Now remember, the indefinite integrals call that because of the plus c. In just the standard problems, you have no idea what the constant is. There's no way to know, so you just leave the plus c in there. But sometimes they'll give you some more information, and that extra information allows you to figure out what c has to be. And I'm going to end on doing a couple of those. It's not hard. Those solutions are called particular solutions. For example, it says find the particular solution satisfying the derivative of f is 28x cubed minus 8x with an initial condition that when you plug 1 into the function, you're supposed to get 2 for the answer. This is that additional information I was referring to. They gave us some information, and in the end, that extra information is going to tell us what c has to be. But let's worry about the initial condition later. Let's deal with the problem at hand. We need to find out what the function is, and they gave us the derivative. But think about it now. We start off with the derivative, and we want to end up with the function. If you're going from derivative to function, you're doing an antiderivative. When you're going from the derivative back to the original function, that's what we started off this whole lesson doing. You're going to do an antiderivative. So what they're saying is, I've got to take the antiderivative of this original f prime so I can get f. So I'll do an antiderivative. And again, that f of 1 equal 2 is the additional information that's going to allow us to find c. So I figured out that I started off with the derivative, and if I take the antiderivative, I'll go back to the original function f. And the reason I know I want to go back to the original function f is because they tell us some additional information about f, and that tells me I need to find f. So I'll do it. 28x cubed minus 8x, I got to do the antiderivative. I know how to do that. I've done it several times. You take the 3, bump it up to 4, divide by 4. The 28 stays where it is. Then you move over to the 8x. You bump that's an understood 1. You bump it up to a 2, divide by 2. The 8 stays where it is. And you end up with 7x x to the fourth minus 4x squared plus c. Now, if you didn't have any additional information, that would be your final answer. That's as far as you can go. You have no idea what c is. You just have to leave plus c in there. But because they gave me this additional information that f of 1 is equal to 2, I can figure out what the constant is by plugging 1 in here, here, here for x. And whatever I get, it's got to come out to be an answer of 2, so I can figure out what c has to be. So I can go off to the side, take that information that I know that when I plug 1 in for x, I get an answer of 2. So I plug 1 in for x. 1 to the fourth is just 1. 1 squared is 1, so I get 7 times 1 minus 4 times 1 plus c, which is 7 minus 4 is 3 plus c. But in the end, it's got to come out to be equal to 2. So I can figure that out now. I can do the arithmetic. I get 7. I get 7 minus 4 plus c is equal to 2. Well, 7 minus 4 is 3. I just said that earlier. So that's 3 plus something is equal to 2. Well, if you subtract 3 from both sides, you'll see that c has to be minus 1. So now I know, after doing a little bit of extra work, but not a lot, now I know that c has got to be equal to minus 1. So that gives me a particular solution of 7x to the fourth minus 4x squared minus 1. Notice that the c has become minus 1 because I have this extra information up here that I can use to figure out what c is. Let's do one more of those. This one looks similar yet different because this time it doesn't say f prime is equal to something. It says f double prime. It says the second derivative is equal to something. And they're giving us an initial condition involving the first derivative and the function. Well, think about this a minute. You start off with the second derivative. You go to the first derivative, then you go to the function. So what that tells you is you're going to have to take the antiderivative twice, or the integral twice. You're going to have to integrate it or take the antiderivative once to go from f double prime to f prime, and then you're going to have to take the antiderivative again in going from f prime to f. So it's the same thing we did in the previous problem, except we've got to do it twice. The first antiderivative gets us from f double prime to f prime, and the second antiderivative gets us from f prime to f. And each time we move, we get a constant, and so we have an extra piece of information that we're going to need. So what that tells us is that we need 2 antiderivatives and a second, which is an extra initial condition beyond what we needed in the previous problem. If we're going from a derivative to a function, we need 1 piece of extra information to find out all the constants. But if we're going from a second derivative all the way to the original function, we've got to have 2 initial conditions. And that's why you've got this one and this one. Now that we know what we're headed for, let's just do it. If we start out with the second derivative and take the antiderivative, we end up with the first derivative. So the first integration takes us from the second derivative to the first derivative. Well, the second derivative is just 2x, and we've done that so many times now. It's going to be an x squared divided by the 2, and the 2 that was already there stays there. You're going to get x squared plus c. So we've got a constant popped in there, and we know that if we use some of the extra information, we can find out what that constant is. Well, what we have is that f prime of x is equal to x squared plus c, but we also know that when we plug a 0 into the derivative, we're supposed to come out with an answer of 1. So if we plug 0 in for x, we're supposed to get 1 for the answer. So if we plug a 0 in for x and get 1 for an answer, that means c has to be 1. So that tells us that this c right here is really just the number 1. So we end up with the derivative being x squared plus 1. So we've used this piece of extra information. The one we haven't used yet is this one. and that involves the function f. So to go from f prime to f is another antiderivative or another integration. So now I need to go from f prime to f. I want to go from f prime to f. I do that by taking another antiderivative. Well, f prime is this x squared plus 1. Term by term, it's going to be 1/3 x cubed plus x plus c. Again, I've got this constant popping in. Is that a problem? No, because I have some extra information up here that's going to allow me to figure out what it is. It says if I plug 0 in for x into the function, I'm supposed to get 3 for the answer. So if I plug a 0 in for x here and here, I'm supposed to get 3 for an answer. Well, if you look at that, that means that c has to be 3. So now I know that this c right here is actually the number 3, and I end up with 1/3 x cubed plus x plus 3, and that's the particular solution. The ideas are fairly simple if you understand everything you were doing for antiderivatives earlier with the capital F notation. We're not doing anything different here, we're just changing the notation. And you can understand antiderivatives by thinking of them as being the reversal of the process that we did when we took derivatives. So I think between understanding what you're doing, grasping the new notation, starting to learn how to use these formulas that we'll be pulling out and learning, between all those tools, all the conceptual understanding, and a lot of practice, this is really not that bad.